Hi, everybody. Let's get back to chapter 3. Uh, this one is the series 4, still on the circuit analysis and transmission lines. Let's take a look at problem 3.23. A discrete resistor with R equal to 200 ohms is inserted into a transmission line with ZS or the source impedance equal to characteristic impedance equal to 50 ohms. Determine the magnitude of the voltage pulse deflected from the resistor. Find the magnitude of the voltage that appears at the source after a delay time of Td equal to L over C, where C is the velocity of the pulse, the transmission line, and L is the length of the transmission line. Okay, so we continue since, sorry, we already give you lectures before. This is just show you examples. Well, you know that what they ask for is the magnitude of the voltage pulse reflected from the resistor. You have a forward voltage VF equal to ES over 2. That's the same voltage divider. And for VB, that's going to be your voltage divider as well. And you have a divided from VF, and that's ended up with ES over 3. Now, that's going to be what? The magnitude of the voltage pulse reflected from the resistor. The next one is to find the magnitude of the voltage that appears at the source. So we look at the source. For T is greater than Td, your V, you already have this equation according to equation 3.60. Just plug in number R equal to 200 ohms and Z0 is 50 ohms. So you end up with V equal to 5 ES over 6. Okay. Problem 3.24. A capacitor with C equal to 2 microfarad is placed across the end of a 72-inch long line. If with ES equal to 4 volt, write an equation describing the voltage at the source after T equal to L over C. In this case, you have the termination is the capacitor instead of a resistor. And we worked out on the equation before, 3.61. You have V equal to, that's one actually VF. In this case, your source impedance equal to characteristic impedance. That's why you have VF equal to ES over 2. And you just plug in number. You have ES, that's 4 volt. And you have the capacitor, the capacitance given, right? 2 microfarad. And Z0, that's 50 ohms. So you end up with V equal to this equation. Now you just take a look quick at T equal to 0. What do you have? When T equal to 0, this term becomes 1. So V becomes 0. So that's true because the voltage just arrived the capacitor, and at the beginning the capacitor is not charged yet. So you have the voltage of the capacitor, becomes 0 at T equal to L over C. For the time being, the capacitor still start charging, and then finally at T go to infinity, it's going to reach uh, the final voltage, which is the ES over 2. So from this equation, when your T go to infinity, this term drop. So you have on left is 2. So that's why you have the voltage, the final voltage become 2 volt. That's um, the voltage at the source. Problem 3.25, replace the capacitor in exercise 3.24 with a discrete inline inductor L equal to 120 microhenry, position at x equal to L. Write an equation describing the voltage at the source after T equal to L over C. Okay, in this case you have a L termination. We already have equation we derived for the total voltage before, according to our equation 3.62. And you just plug in the number, you have everything. Your L is the 120 microhenry. That's 120 10 to the negative 6. And this is your final equation, the final voltage at the source for the time being. Same thing. You can consider at the beginning t equal to 0, and this one become 1, right? So let's make 4 for the total voltage. And that's the total voltage at the source when you just start. For let's see what we have here. Okay. And then for the time being, t go to infinity. Sorry, this term drop. So you have the final voltage to be 2 volt. Okay, let's come back to V forward, which is the ES over 2. Okay, that's uh, our determination by using R, L, and C. Let's take a look at the new topic 3.11, characteristic impedance of conductors, or C0, for different type of uh, transmission line. The first thing we are talk about are coaxial. Coaxial. We have the inner insulation and dielectric. Okay, and you have the central conductor with the radius A, and the outer radius is B, and you also have outer insulation. This is the cross section of a coaxial cable, of typical coaxial cable. In this case, you can find characteristic impedance Z0 equal to this equation 3.63, where mu is the permeability in the unit of Henry per meter. That's related to the magnetic property, and epsilon is permittivity farad per meter, related to uh, electrical property. The next one is wire transmission line. If you have the conductor uh, above the ground edge, and the wire have dimension or diameter d, this is your Z0. The next one is the transmission line on circuit boards. This is a microstrip lines on a PCB or printed circuit board. You have a ground, and this one is the circuit trace. Okay, that's you send the signal through this the copper. Okay, that's the circuit trace uh, located on the PCB, and we're going to define the thickness in the term of the weight. That's mean if you have the copper 1 ounce copper cladding, your thickness is going to be 1.4 mil, and for 2 ounce copper cladding, the thickness is going to be 2.8 mil. And your characteristic impedance of this microstrip line is going to be according to equation 3.65. You know everything epsilon r, that's the relative permittivity, and h and the u and t according to this figure. And you also can be able to find how velocity along the microstrip line, c equal to 1 over square root l prime c prime. And you know l prime is the distributed inductance, and C prime is the distributed capacitance. This is in general form. And also you'll be able to find the propagation delay, which is the 1 over C, according to equation 3.67. So whatever is depending on what kind of transmission line you have, you just pick up equation, to find your characteristic impedance. And for this microstrip line, you can also be able to calculate directly from relative permittivity according to equation 3.68. Next one is microstrip line in multi-layers PCB. You have a power line here, you have ground line plane here, and you have your copper cladding in the circuit board. Your characteristic impedance going to be this equation, and this is your TPD, that propagation delay time in the unit of per nanosecond per feet. The next one is the topic 3.13, resistance of printed circuit lines. You are going to be your rho L or WT. You're probably familiar with this already, so I don't need to explain. And for copper cladding, 1 ounce, the thickness is going to be your 0.00135 inch. So you can find the ratio of R over L, the resistance over the length of the copper. That's give you a distributed resistance, right? Per. And do the same thing for the thickness of 2 ounce. Now let's take a look at some examples. Problem 3.26. A bare copper wire is used as a telegraph line connecting two locations 100 mil apart. The wire is strung on posts, and on the average, the wire is 20 feet above the ground. Okay, you have the wire uh, 20 feet above the ground. If the groundwater is an average of 10 feet below the surface, determine the characteristic impedance of the line. Note that the groundwater serves as the second conductor of the transmission line. You can apply your this type of transmission line. This is your characteristic impedance. Okay, we need to just plug in number. What is your epsilon? In this case, the we're talking about air. For air, epsilon equal to epsilon r, epsilon 0, but epsilon r equal to 1 for air or free space. And your epsilon 0 equal to 8.85 10 to the negative 12 farad per meter. And your H simply become a 20 plus, I think I did this one wrong, sorry. It's supposed to be 20 plus 10. So that's give you what, 30, right? Anyway, you can correct this there by yourself. And 1 feet equal to 0.3048 meter. And D is 100 mil. And 1 mil is 1 over 1,000 inch. That's give you 0.00254 meter. Because 1 inch equal to 0.0254 meter. And finally, you have Z0 become 2.03 10 to the 8th ohm. Very large. I don't understand about this one, but it's just, example. Problem 3.27. A Teflon insulated wire with epsilon r equal to 2.3 is supported by a copper ground plane. The wire is 22 gauge with D equal to 0.032 inch, and the diameter of the Teflon insulation is D equal to 0.062 inch. Estimate the characteristic impedance of this wire. Okay, just pick up equation 3.63 because this is coaxial. Since the Teflon is a non-magnetic material, for permeability, mu equal to mu r relative permeability, and mu 0, mu r equal to 1, and mu 0 equal to 4 pi 10 to negative 7 Henry per meter. And epsilon equal to epsilon r, epsilon 0, epsilon r is given. That's the 2.3. Okay. So finally, you have Z0 to be 26.815 ohms. Some of them you probably familiar. That's their 75 ohms, right? For coaxial. Problem 3.28. A microstrip line divided in figure 3.21 is etched with a width W equal to 10 mil in copper cladding with a thickness of 2 ounces per feet square. The glass epoxy laminate separating the line from the ground plane is 60 mil thick. Determine A, the characteristic impedance Z0, B, the distributed capacitance Z prime, C, the distributed inductance L prime, and D, the signal velocity. Take a look at the figure 3.21, this figure. Okay, you have Z0. For 2 ounce copper cladding, you have the thickness to be 2.8 mil. And for glass epoxy laminate, epsilon r equal to 4.7. You end up with your Z0 equal to 128.3 ohms. This one you have everything, so I don't need to explain. Now our C prime distributed capacitance. Well, you need to go to figure 3.22. And there you have like width, W equal to 10 mil. And dielectric thickness, sorry, H equal to 60 mil or 0.060 inch. Let's go to figure 3.22. Right, I think 3.22. Okay, it's coming up. Yep, it's this one. Okay. Our this is the line width W, right? What do we have just now? Let's hold on a second. The line width is what? 10 mil. Just take a look at this point, okay, on the x-axis. And what else? You need to choose what is your dielectric thickness, or the spacing. That's 60 mil. We don't have 60 mil here. 60 mil, that's about 0.06 inch. So it's somewhere around here. Okay, you can do just approximation. And I put this one as what? 15. Actually, it's supposed to be what, 25? And the unit is the picofarad per feet for capacitor. Let's see. Okay, let's get back to the problem. Well, you can do approximation. Let's assume that I have C prime equal to 15 picofarad per feet. And what about C? The distributed inductance L prime. Well, you can look for L prime on from Z, the relation of Z0 characteristic impedance equal to, this is in general form, equal to square root of L prime over C prime. So your L prime simply Z0 square C prime. You already have a Z0, that's the 128.3. And your C prime, you already have 15 picofarad, that's the 10 to negative 12 farad per feet. You end up with L prime equal to 228 nanohenry per feet. Okay. Next, sorry, the signal velocity C equal to 1 over square root L prime C prime. According to equation 3.67, you can look back at this equation. We have C equal to 5.41 10 to the 8th feet per meter. Okay. Problem 3.29, a strip line divided in figure 3.23 with W equal to 5 mil is fabricated from 1 ounce per feet square copper. This line is embedded between the two ground planes with a spacing B equal to 20 mil. Determine the same four quantities as indicated in exercise 3.28. There were for a strip line in multi-layer PCB. You have this one. Yep. This is your Z0 equation at 3.69. A, epsilon R, B, W, T. Just plug in number. But this one is the 1 ounce. So the thickness turned out to be 1.4 mil. You have Z0, 54 ohms. And C prime, you do the same thing. Go to figure 3.22 with W 5 mil, H equal to 20 mil, 0.020. I have C prime about 30 picofarad per feet. And distributed inductance, just plug in number, Z0, C prime. So you have L prime, distributed inductance, 87.5 nanohenry per feet. And this is your signal velocity, c equal to 1 over square root l prime c prime. We have c equal to 6.17 10 to the 8th feet per second. Okay, that's all for series 4. And we finished chapter 3. Uh, I will let you know what's going to be the next chapter.